Hello, and this is Sunny. Welcome back. First, I'd like to apologize for making a mistake in my last video. Step 3 should be decryption by Alice, the message receiver, not a key generation. It is a big mistake. I apologize for causing some confusion. Last time I talked about how the RSA works with math formulas. Today I will demonstrate how it works with one simple example. The RSA process involves 3 major steps. Step 1. Alice, the message receiver, will generate a pair of keys, one public key and one private key. Alice sends the public key to Bob. She keeps the private key. She never shares her private key. Step 2. Bob, the message sender, will use Alice's public key to encrypt his message and send the encrypted message ciphertext to Alice. Step 3. Alice uses her private key to decrypt Bob's ciphertext. Now let me demonstrate the whole process with some simple numbers. Step 1. Alice generates a pair of keys, a public key and a private key. These 2 keys are mathematically related, and this step involves many sub-steps. Here we are. First, Alice selects 2 prime numbers for P and Q. For example, P is 2 and Q is 7. In real implementation, these 2 prime numbers are tremendously large. Then we calculate n and use the formula n equal P times Q. Thus, n is 14. When I use way or less in my explanations, it means Alice or Bob, depending the context. The next sub-step is a little bit complicated. We calculate the phi function n. The phi function is to get all prime numbers with 14. This means from number 1 to 14, we will find all numbers that are co-prime with 14. Please refer to my previous video if you want to know what co-prime means. Thus, co-prime numbers are 1, 3, 5, 9, 11, and 13. There are 6 co-prime numbers with number 14. It's much easier to use this formula to find the number of co-prime numbers with 14. The phi function of n is p minus 1 times q minus 1 equals 6. And 6 means these 6 numbers. So 1, 3, 5, 9, 11, 13. Next, let's select integer e from these 6 numbers, 1, 3, 5, 9, 11, and 13. Where the integer e must satisfy 2 conditions. Condition 1 is e is bigger than 1 but less than 6. Now only 3 and 5 are good. The second condition is that e and 6 are co-prime. 3 is not a co-prime with 6. Now only 5 is good. Thus e is 5. We got e and we know n. Thus we got the public key 5 and 14. That's a public key, and Alice sent the public key to Bob. Now let's calculate d. We plug E and A into the formula. Phi D means phi times D modulo 6 equal 1, which means phi times D divided by 6, the remainder is 1. D can be one of many numbers satisfying this condition. And D can be, for example, D can be any of 5, 11, 17, 23, 29, 35. You can see there's many numbers which satisfy this formula. We choose 11 for D. Then we get a private key N and D, which is 14 and 11. That's a private key. Alice will keep this private key for decryption. The end of Alice key generation. Step 2, encryption by Bob, the message sender. Suppose Bob wants to send his message K to Alice. K is an alphabetic letter and is in plain text. To use the formula, we must convert K to a numeric value. For example, both Alice and Bob use this table to convert an alphabetic letter to its numeric value, or vice versa. Plain text K is converted to its numeric value, which is 10, and 10 is less than 14. Great. And let's use this formula to get ciphertext for 10. And we get C equal 12. And 12 is a ciphertext for the plain text 10. And Bob sent 12 to Alice over the public channel. Now the third step, decryption by Alice. And Alice will use her private key 14 and 11. And plug the ciphertext 12 in the formula, and Alice gets 10. And Alice used the table to convert 10, she gets K, which is Bob's original message. The whole process, encryption and decryption, is done. I hope this video is helpful. Thank you very much, and see you next time.